Good afternoon, ladies and gentlemen. Today we're going to be talking about the natural base E. Now, I really want to go into this very specific story to entertain you all regarding the story behind why we call it the natural base E, specifically why we use the word natural, right? So let me go ahead and jump right into that and tell you all about why we actually call it natural. And I found this article is really interesting, and I kind of want to read I kind of want to highlight some things to you all. So first of all, E is a constant. E does represent a number. It is not a variable, right? And that number is 2.718, so blah blah, so on and so on. It goes on to infinity, which makes it irrational. Now, if you remember, an irrational number is a number that cannot be denoted by a fraction, right? Because a fraction is a rational number. So that's the difference between irrational and rational. Now, I want to highlight this example because this example really encompasses what we've been learning about in terms of compound interest, in terms of exponential growth, and so on, right? So, say the case where you are at a bank and the bank is, you put money in the bank and the amount of money that you put in the bank is $1, right? So, the bank offers you 100% interest rates, right? So they're actually going to give you 100% of the money that you store in once a year. So if you store $1, if you're going to get compound interest once, and you're going to get 100% of it, so obviously $1 plus $1 will give you $2 at the end of the year. And say that you're actually going to still get 100%, but this time they do it twice a year, right? So the first time around, you're actually going to get from $1, you're going to go all the way up to um, 1.5, right? Because half a year you only got 50%, so 50% of $1 is 50 cents, so 50 cents plus that $1 is 1.5, right? But now if you 50% 1.5, you actually get 0.75 the second half of the year, right? So now 75 cents plus $1.50 actually equals $2.25. Notice the difference, right? You got compounded twice, and here you got compounded once. Still 100%. The ratio does not change, right? The percentage didn't change, but now you get more money. It's $2 versus 2.25, right? Say you get on compound interest every 4 months, right? So the end of the year you're gonna have 237. Say you get compounded every single day and you get this very beautiful number, right? And say you even want to get closer and you want to do every second. There are, and this is kind of interesting, these are the amount of seconds that there are in the year, and you actually get really close to that number, which is E, right? So let's compare that number. We are actually very close. So this is how exponential growth works. I don't really want to talk about the calculus parts. For those of you who know about that, we will see that soon. Well, not in our class, but in calculus, you will see that. These are some pictures where you can see that spiral form. So here we have a Cartesian plane. This is what E looks like, but if we put it on the polar coordinates, it actually looks like this, right? So these are some pictures that denote that, the natural form, right? And you actually see patterns like this in our universe, right? You can tell right away that all of these look like E in the polar coordinates. So that's something very interesting that I wanted you all to just know in terms of why we call it the natural base E. Now, in terms of the mathematics, so what I want you to know with the natural base E is actually just to be able to manipulate the functions and use them appropriately. So here, if we're multiplying two expressions with the same base, then you know already that, well, we already have the same base, so all you got to do is add the exponents. So 3 plus 6 will give you 9. Pretty straightforward, right? Here you keep the coefficients together, and you keep the natural base e together, right? So here we're going to subtract 5 minus 4, and here 16 divided by 4 is 4, so we get 4e to the 5 minus 4, which is just 1, so we get 4e, right? We're following the same rules that we've been working with exponents all this time. When we have a exponent to an exponent, what do we do to the outside exponent, right? So some of you, I remember saying, you kind of distribute that exponent, right? So 3 to the second power and e to the negative fourth x to like doubling it, right? You're multiplying that. So you actually get 9. Oops, let me go ahead and move away from that. You actually get 9, and here you get negative 8x, right? Because you're doubling it. That's what it means to distribute back in that exponents.